When we are going outside, we often check the weather app, and you'll notice there are two numbers. One tells us the actual temperature, and the other tells us the feels like temperature. Those two numbers are not always the same. The temperature sometimes we feel is not always the same as the temperature that is measured. Wind, humidity, and sunlight can all change how heat moves between a body and its surroundings. So, temperature alone cannot explain how the air feels. Let me introduce you to my buddy, the hairless cat. To understand the feels-like temperature, we need to look at how heat moves between the cat's body and the environment. The key idea is simple. What the cat feels depends on how fast heat enters and leaves its body. If heat enters faster than it leaves, the cat heats up. If heat leaves faster than it enters, it cools down. So, what matters is the rate of heat transfer. To describe everything happening to the cat, we use this heat balance equation from the first law of thermodynamics. Think of this as tracking all the heat going into and out of the cat's body. Qmet is the internal heat the cat's body generates. Qrad-in is the sun shining on the cat, adding heat to its skin. Qconv is the air carrying heat away from the cat's skin. Qevap is the water on the skin evaporating and removing heat. And Qradout is the heat the cat's body gives off to the surroundings. All of this equals dQ body over dt, which determines whether the cat is actively heating up or cooling down. To make this model practical, we simplify it. The cat is just sitting still, so there is no mechanical work or motion. We assume Qmet is small compared to the sun and the environment. We also assume minimal contact with the ground, so conduction is ignored. This allows us to focus entirely on the environmental effects. Now imagine the cat's skin is slightly wet. When water evaporates from the cat's skin, it pulls heat away, which helps cool the body. This process can be described by this equation, where Q.evap represents the heat removed from the cat due to evaporation, M. is how much water leaves the cat's skin, and LV is the latent heat of vaporization, which represents how much thermodynamic energy each drop needs to escape. As more water evaporates, more heat is removed. In dry air, the relative humidity is slightly low, approximately 30%. Water can easily evaporate from the skin. In this case, M. becomes higher, so the cat cools down effectively. However, in humid air, the air has higher relative humidity, around 60%. The environment is already full of water vapor, M. is lower, so less water can evaporate. As a result, less heat is removed, and the cat feels hotter. On windy days, the cat's skin warms the air around it, creating a thin boundary layer of warm air surrounding its body. When the wind blows this layer away, it removes this warm layer and replaces it with fresh air. This increases the rate of heat transfer, allowing heat to leave the body faster. This process is described in this equation, where Qconv is the heat transfer by convection. H is the convection coefficient, which represents how strongly the wind enhances heat removal. A represents how much of the cat's skin is exposed, and T-skin minus T-air is the temperature difference between the cat's skin and the air. This term decides the direction of heat flow. Usually, as wind speed increases, more heat is carried away, so the cat feels cooler. However, notice the temperature difference in the equation. If the surrounding air becomes hotter than the cat's skin, then the heat no longer leaves the cat. Instead, the hot moving air transfers heat into the cat's body. So in that case, wind does not cool the cat, it makes the cat feels hotter. Another scenario, the cat sitting under direct sunlight. The sun adds heat directly to the cat's skin through radiation. This process can be described by Qrad equals epsilon times sigma times A times the quantity, T to the fourth power, minus T of the environment to the fourth power, where the amount of heat transfer depends on the temperature difference between the cat and its surroundings. If the surroundings are hotter than the cat, this means the cat can gain heat even without direct contact or moving air. As a result, the cat absorbs extra thermal energy and feels much hotter. Now we combine everything to understand the overall effect. Humidity reduces evaporation, which means less cooling from the cat's skin. Wind usually increases heat loss by enhancing convection, allowing heat to leave the body faster. At the same time, the sun adds heat through radiation. We can summarize this using net heat transfer, where heat coming into the body is compared to heat leaving the body. Q.net equals Q.radin minus the sum of Q.conv plus Q.evap plus Q.radout. In this equation, the heat entering the cat comes directly from the sun. The heat leaving the cat escapes through convection, evaporation, and the body's own outgoing thermal radiation. If the net heat transfer is positive, heat enters faster than it leaves, so the cat heats up and feels hotter. If the net heat transfer is negative, heat leaves faster than it enters, so the cat cools down and feels cooler. All of these factors work together to change the overall heat balance, which ultimately determines the feels-like temperature. In short, the thermometer only tells you the air temperature, but what the cat feels depends entirely on heat transfer. The feels-like temperature is determined by the thermodynamic balance of heat transfer between the body and the environment. Thank you for watching. If you have any feedback about this video, let me know.